Hi friends, welcome to GMK tutorials. In this video, we are going to see about the constant voltage scaling. Right? So previously, we discussed different types of methodologies for sources of power dissipation and device feature size dimensions reduction techniques. And that one, first one is nothing but a constant field scaling. Second one is nothing but a constant voltage scaling. Generally, in case of the constant of field scaling, if you are reducing the supply voltage and frequency of the corresponding circuit, obviously the total power dissipation is also decreased by some factor s square. But the problem is that if you are still reducing the power supply voltage to the minimum voltage, but some of the devices may be operate for only high voltages. So, okay, so that is a basic intention why we are coming to the constant voltage scaling approaches. Let us see the first one. So in a constant voltage scaling, all the device dimensions are scaled down by a factor of s, just like a constant field scaling. However, in many situations, the scaling of the supply voltage may not be feasible in practice. So, for example, if you are taking a CPU, so central processing unit, is a scale down to minimize the power dissipation, it leads to electrical compatibility with peripheral devices, which usually operate at a higher supply voltage. So at that situations, there is an issue with respect to the corresponding constant field scaling. So that's why that such a kind of the problems can be avoided with the help of a constant voltage scaling approaches. Let us see it may be necessary to use the multiple supply voltages, complicated level translators to resolve such a type of problems. But if you are increasing such a kind of the complexity in the circuit, it leads to the drawback, which maybe increases the area of the device and performance maybe decreases. So that is some of the considerations. So let us see some more points regarding this one. In such a situations, constant voltage scaling may be preferred. In constant voltage scaling approach, power supply voltage and threshold voltage of the devices are maintains a constant value. Previously, in a constant field scaling approach, both the supply voltage and the threshold voltages are reduced to the some extent to maintain the power dissipation is very low. But such a kind of the situations, some drawbacks will be find out in that method. For that purpose, we will come to the constant voltage scaling approach. In a constant voltage scaling approach, we are maintaining the voltage and supply voltage value as a constant parameter, and we can change the remaining physical parameters, and how the physical parameters or affects the electrical parameter is the main thing. So let us see in that constant to preserve the charge field relations. However, the doping densities have to be increased by a factor of s square. So the key dimensions, voltages and doping densities for a constant voltage scaling are shown in the figure that represents the. So here, so to preserve the constant field relations, however, the doping densities have to be scaled down by a factor s square. The key dimensions and voltages, doping densities are a constant voltage scaling are shown in figure. So first one is nothing but quantity before scaling, after scaling. So first one is nothing but a channel length. So that can be represented as a L before scaling. So after scaling, it can be represented as L dash. So where L dash is equal to decreased by a factor of s square, s, right? That means the length of the channel is obviously decreases to the some extent by a factor of s. So let us see some of the remaining things is nothing but channel length width. Width can be W represented with W. W dash is nothing but new generation width, that is also decreased by a factor of S. As well as the gate oxide thickness is nothing but TOX. TOX dash is nothing but new generation oxide. So that is also decreased by a factor of TOX by S. as well as the junction depth xj can be represented as well as that is also decreased by a factor of s, right? So coming to the power supply voltage, that is also vdd is also maintains the same value because of constant voltage scaling means that we have to maintain the threshold voltage as well as supply voltage, both are maintains some constant values. So doping concentrations are increased by a factor of n square, and second one is nothing but nd is also increased by a factor of n square, right? So the constant voltage scaling results in increase the drain current, because of if you are increasing this increasing the supply voltage means that obviously the drive is also more. If the drive is more means that obviously the corresponding current in case of the MOSFET is also increases. So that in turn increases the power dissipation by a factor of s and power density by a factor of s cube. So let us see the what about the electrical characteristics in case of the constant voltage scaling. So gate capacitance Cg is also decreased by a factor of s, drain current Id that is increased by a factor of s, power dissipation P, that means power supply maintains a constant value but current value is increases. Therefore overall power dissipation in the circuit is also increased by a factor of s, and power density, that is nothing but power for unit area, that is also increased by a factor of s cube, and delay time is also decreased by a factor of s square. These are the some of the electrical parameters with respect to the constant voltage scaling. So as there is no decrease in the delay, there is no improvement in the performance. This increases the power density by a factor of s cube, has a possible adverse effect on the corresponding divisor because of only particular area is also becomes as a hotspot because of the power density is increased by a factor of s square. So this is some of the relations why power is increased by a factor of s. Regarding the linear current is increased by a factor of s, and saturation current is also increased by a factor of s. That can be depicts the relations, right? So in the next video we will see about the architectural level approaches, okay, and how the RTL is used, and parallel processing approaches, and how it is used for the multi-bit adders point of view, okay. So this is regarding the constant voltage scaling. So thank you for watching GMK tutorials. Thanks a lot.